let's load. We have a matrix B that is 1025 by 1025. This is our right hand side. So let's say the center, which is the middle 123 by 123, is our right hand side. We put it as 125 to make up the boundary conditions we need. So let's figure out for that particular, for a matrix like that, how do we code up a Jacobi iteration and how do we code up a Gauss Seidel iteration. So let's first remind us what the Jacobi iteration, oops, Jacobi, not Jacobi. Okay. So let's make up a function that applies the Jacobi iteration for only one iteration. So the input is u0, b, and the output is u1. So here, if we plug in uk to u0, we would get uk plus 1, right? Okay. So we assume that n is the dimension of the matrix. So let me tell you what is the grid I'm doing here. So this is the boundaries. We have values even on the boundaries. So the whole thing is going to be 125 points. That means the interior is going to be 123. Okay, and so if we look at the grids, if you look at the cells, this would be 1, this would be 124, right? So there are 124 intervals and 125 points, 123 interior points. So n interval would be the size of B1, so that's the first dimension of 1 minus 1, right? I get 125 minus 1. And that helps me to compute dx. So let's assume our domain size is still equal to 1. So it's going to be 1 over n. Okay. So what do we need to, how do we apply the Jacobi iteration? We have u1 is going to be zeros, size u0, right? So we make, well, we don't have to do this. We can do minus dx square over 4 times b. So that's that is this term, right? The first term in our iteration. And then for I goes from 1 to n plus, well, we are doing the interior, so 2 to n. And for j goes from 2 to n. We would be doing u1 of ij would be equal to this itself plus the average of the average of, well, this is Gauss Seidel. For Jacobi, the only difference is these are, all of them are k instead of k plus 1, right? So u0 of I minus 1j plus u0 of I plus 1j plus u0 of ij minus 1 plus u0 of ij plus 1. Divide by 4. Let's make this a little bit prettier. So that's what we are looking at. And. So that completes our Jacobi iteration for the matrix. And for example, let's make a u0 to be 0's size of b. So it's the same. And we can do u1 equal to Jacobi u0 and b. So an interval, yeah. Thank you. Oh, no, it works. Okay, so if we do I am sure of u1, it'll be pretty much a dark, right? Because we only applied for one iteration. And what we can do is that let's say u is equal to u0, and we can do basically u equal to Jacobi ub, and we can do that again, that again, that again, right? We can do this again for many times, and we can show I am sure of u. So we start to see some contour. You may be able to see something white about it, right? And I can do for I equals 1 to 100, u is equal to Jacobi u and b. I probably need to put a semicolon so that I don't get crazy output. So I do that. I seems to see an airplane showing up, right? So this is iterative method. As you iterate more, you see the solution closer and closer to something you may look like, you may expect. Okay, so let's try to modify the Jacobi iteration to Jacobi to Gauss Seidel. I'll just call it Gauss. And so what do I need to modify here? Which line should I modify? Line 8, right. And which other terms I need to change if you think about the difference between Jacobi and Gauss Seidel? I just need to change the UK to UK plus 1 for 2 terms, right? And which other terms are already computed? This one and this one, right? The J minus 1 and I minus 1 terms. So that will be all the modification I need to change Jacobi to Gauss Seidel. And again, let's see what the effect is. Okay, so let's do u equal to u0 again. And for I equals 1 to 100, u is equal to Gauss Seidel u and b. Okay, so now let's take a look. Again, we are converging to the solution, right? But the convergence is going to be very slow because now I have an eigenvalue that is cosine of pi divided by 124. That's what I expect to be the highest eigenvalue if I have a 1D Poisson's equation. If I have a 2D Poisson's equation, I would have an eigenvalue that is pretty much 1, right? Format long. That'll give me the actual eigenvalue, not rounded to something that is only 5 digits. So I get a bunch of 9s, and if I do that, okay, I get something times 10 to the minus 6. If I take 1 divide by that, or more rigorously log 2 divide by that, I need something like 74,000 iterations to make the error to be even half. That's a lot of iterations I need. And generally, if you remember the cosine curve at x equal to 0, the cosine curve is like a parabola, right? So if you take a Taylor series approximation, the more n you have, the number of iteration you required would go like n squared. So because I should illustrate that a little bit more. So your biggest lambda is equal to cosine of pi over n, right? So that is approximately 1 minus half, if you do the Taylor series expansion, pi over n squared. Okay, and my number of iterations required would be proportional to 1 over 1 minus lambda or log 2 over 1 minus lambda, which is log 2 divided by half of pi over n squared. So that goes like n squared. If you double your grid points, you should quadruple your number of iterations to converge to the same accuracy.